Look at intra and intermolecular forces. But before we get into that, let's do a little bit of a review from yesterday's lesson. Polar molecules dissolve in other polar substances. This means that they are miscible. Nonpolar dissolves in nonpolar. Nonpolar molecules are blank in polar solvents. Immiscible. Okay, I want us to take a moment and determine whether each compound is polar or nonpolar. Should be able to do this in a minute. The code that you should get is 1, 2, 2, 1. Yay. The learning goals for today. We are going to be able to tell the difference between intramolecular forces and intermolecular forces. Intramolecular forces are inside the molecule, aka the bonds. So we've been looking at this. The bond character, is it ionic, polar covalent, nonpolar covalent? This is an intramolecular force. Then we're going to take a look at intermolecular force. These are the forces between a molecule and another molecule, okay? So it's between other molecules. And remember yesterday, whenever I refer to the word molecule, I am talking about a molecular compound. Okay, let's take a look at the difference between an inter and an intramolecular force. Let's first start off with intra. Intramolecular forces are in molecular compounds. The forces in a molecular compound are between atoms in a molecule. Okay, they're between atoms in a molecule, also known as the chemical bond. So the physical bond between an atom and another atom. For example, in methane, which is CH4, the bond between carbon and hydrogen is considered an intramolecular force. Okay, this bond between carbon and hydrogen has a 0.4 electronegativity difference. Okay, so it has a electronegativity difference of 0.4, giving the bond a nonpolar covalent characteristics. So because of that electronegativity difference, this bond here, highlight this bond right here, is a nonpolar covalent bond because it has an electronegativity difference of 0.4. So we've already been talking about intramolecular forces. We are now just giving that a name. Okay, so in molecular compounds, this is what is meant by an intramolecular. In ionic compounds, we have this thing. So intramolecular forces in an ionic compound, we have this force called electrostatic force. Electrostatic force. Okay? This force is the strongest force that we can have. And it happens in ionic bonds. Okay, so this is the strongest force of all compounds. The basic definition of an electrostatic force is that atoms with opposite charges will attract each other. If you've ever heard that saying, opposites attract, from chemistry, you can thank chemistry for that. Atoms with the same charge will repel each other. Okay, let's move on to intermolecular forces, specifically in in molecular compounds. Because it says it's intermolecular forces, what that means, think of it as an international connect, okay? It's leaving the molecule to make an international connect. So, AKA an international connect. Those are two ends. Inter. These are forces that cause molecules to attract to each other to form solids and liquids. So basically what happens, as your intermolecular force strengthens, or as the temperature decreases, your intermolecular force is going to get stronger and stronger. A solid and a liquid is formed when molecules stick together. As soon as they start becoming larger clumps, they have a phase change. Okay, so if gases that are cooled enough, they will eventually stick together and turn into a liquid. If I cool it even further, that bond is going to solidify and it'll turn into a solid. Okay, let's look at what intermolecular force looks like. So for example, let's take water, okay, H2O. Let's draw a Vesper diagram for that. I'm going to use this whole space for it. So we have hydrogen bonded to an oxygen, bonded to a hydrogen, and then we have another molecule here. Okay, remember an intermolecular force happens between two molecules. Now, let's draw our dipole moments on here. So we have our arrow pointing towards oxygen on both sides, which makes hydrogen partially positive and oxygen partially negative. Let's do the same to this other molecule here. Okay, towards oxygen, partially negative, partially positive, partially positive. Now, we talked about how opposites attract, right? So what's going to happen is this negative pole on the oxygen is going to attract this partially positive hydrogen, and they're going to form an intermolecular, and an intermolecular force will be present between them. Okay? As the temperature will go down, that force will strengthen, and eventually those water molecules are going to stick together, and it'll change into liquid. Okay, so an intermolecular force is the ability to attract another molecule. They're making an international connect. So, to summarize, the partially negative pole on the molecule, which is the oxygen with the partially negative charge, will attract the partially positive pole on another, very clear here, it's on another molecule. Okay, so it's on another molecule. Okay, there are three main types of intermolecular forces that are found in molecular compounds. These do not exist in ionic compounds, okay? The overarching name for all of these forces is, it's called van der Waals forces, okay? So he's the one who's come up with them. So he has taken the overarching umbrella for all three types. The first one is called London forces, or I may refer it as London dispersion forces, okay? For short, I will be calling them LF. Now, London forces exist in anything that has electrons. The more electrons, the more London force you will have, okay? So it's present in all molecules, because all molecules have electrons. So basically, anything with electrons. So basically what happens is there's a temporary uneven distribution of electrons, which allows us to have a temporary pole form on a molecule, which allows for the intermolecular force to form between molecules, okay? So there's a temporary uneven distribution. Oh, that one's spelled wrong. Distribution of electrons. More electrons equals more London force, and this is the weakest force that we have. Very weak. The next one is called dipole-dipole forces. We will shorthand them for DD. So whenever I'm referring to DD, it is a dipole-dipole force. So it's called dipole-dipole for a reason, because it only exists in polar molecules. Okay, so first thing, it's present in polar molecules. Okay, so anything with a net dipole. Okay, this is a permanent uneven distribution of electrons. So notice how we form a partially negative side and a partially positive side on a polar molecule? That's okay. So in dipole-dipole forces, there is a permanent uneven distribution of electrons. If I can spell this word right today, it'd be great. Distribution of electrons. Okay, forming that partially positive, partially negative side, which allows us to attract more molecules to each other. Okay, this is a much stronger force than London forces. So stronger than London forces. Again, because we form those poles, it allows it to attract other molecules. The last van der Waals force is called hydrogen bonding. I will refer to it as HB. Again, this is a permanent distribution of electrons. Okay, so now, very specific. Hydrogen bonding only happens if it meets the following requirements. If there is a bond directly between fluorine and hydrogen, that is considered hydrogen bonding. If there is a bond between oxygen and hydrogen, that is considered a hydrogen bonding. And the last one, nitrogen between hydrogen. That is the requirement for hydrogen bonding to happen. If it is not directly connected to that hydrogen, it's not considered hydrogen bonding. Okay, so to summarize this point, hydrogen needs to be directly, hydrogen needs to be directly connected to fluorine, oxygen, or nitrogen, which is shortened for FON. F-O-N. FON. Okay, I'll pause and then. Hydrogen bonding in a molecular compound, as I said, is the strongest bond. Okay? Strongest in molecular compounds. What's the strongest overall? Ionic bonds, because it has an electrostatic force. We're not working with partial charges there, we're working with full charges. Okay, I'm going to draw the Lewis dot diagrams here and you'll help me identify the shapes. We have ammonia here, ammonia. It looks like this. I've noticed that some of you have started cheating with your Lewis dot diagrams. We're not there yet. You still need to count the electrons, okay? So, what shape will this form? Pyramidal, because it's that lone pair is forcing those bonds down. So this is a trigonal pyramidal. Okay, let's draw the Vesper shape. Looks like this. Okay, with dipoles. By dipole pointing towards nitrogen or hydrogen? Nitrogen. Okay, and the arrows are the same strength. Polarity of this compound, polar or non-polar? It's polar. It doesn't meet the first requirement of being group 14. Okay, they should say London forces. So everything has London forces. Anything with an electron has London forces. This has dipole. Why? Because it's polar. It has a net dipole. And lastly, does this have hydrogen bonding? Yes, because we have hydrogen directly connected to nitrogen. Okay, moving on to the next one. Lewis dot diagram looks like this. I know this because I counted the electrons. You did not count the electrons, you tried to cheat. That's what I know. Oh, when I see you do it, I'll point it out. Okay, the shape name has two lone pairs, two bonds. Bent or angular, but since I'm not good at spelling, we'll go with bent. Okay, because it's bent, please physically show that it's bent. Do not draw a straight line of atoms. I can't give you the mark then, because you drew a linear Vesper shape. Please identify that it is bent. Dipole moments towards oxygen or chlorine? Oxygen, right. Polar or non-polar? Polar. Everything has London forces. Does this have dipole? Yes. Hydrogen bonding? No. Okay, last one together, and then we will stop the lesson there, and then you'll do the last one on your own. Silicon tetrafluoride looks like this. Drawing dots again, guys. What shape does this make? Tetrahedral. Okay, with the tetrahedral, we have two of our peripheral atoms in the plane. We have one that is coming forward or at us, and then one that is hanging out in the background. Does this have dipole moments? Yes, it does. Which one should it point at? Bromine. Good. Okay, of equal strength. Negativity difference is the same. Polar or non-polar? Non-polar. Okay, London forces, yes or no? Dipole-dipole? Hydrogen bonding? No. So out of the three examples we have done, which one has the weakest intermolecular force? Hold on. 1, 2, or 3. Which one has the weakest? 3. Who's the strongest? 1. Good. Okay, do the last one on your own. Get me to check, and then you're doing your homework for today. We're going to go through and look at the most common mistakes that were made. I want to go through it together just in case you make these mistakes at home. You'll know what's going wrong. Okay, first of all, the Lewis dot diagram, how many total valence electrons should I have? 12 electrons. When I count on this diagram, 2, 4, 6, 8, 10, 12, 14, I have too many. This is what I mean by cheating. You didn't calculate the number of total valence electrons. So how do I fix this problem? Double bond between who? Okay, so it's going to look like this. Because you made your Lewis diagram incorrectly, you put the wrong shape for it. What shape should it be? Trigonal planar. So everything needs to be in the plane, okay? So that affects the way that we draw our shape. Oh, why is there nitrogen going on here? Oh, I'm so used to drawing ammonia like that. Hold on, let's fix this. Okay, so this is incorrect. So we should have carbon in the middle, Chem 20, and hydrogen, oxygen. The orientation doesn't matter, but the angle does. It should be roughly 120. Now, is this polar or non-polar? Polar. Okay. This is where a lot of confusion happens. Because carbon is group 14, that meets the first requirement. The second requirement is, are my peripheral atoms all the same? No, because they're not all the same, it becomes polar. Okay, and you can do vector addition, you can get a net dipole, and that'll prove why. So everything has London forces, there's nothing wrong there. Does this have dipole-dipole? Yes. Does this have hydrogen bonding? Absolutely not. This hydrogen here, is it bonded to this oxygen? No, so you can't have hydrogen bonding. Okay? 1 minute.